Well, good morning, ladies and gentlemen. Thank you very much for being here and listening to our quantum thoughts. You know what they say about quantum? They say that it's the dream of theoretical physicists and mathematicians and the nightmare of engineers. Okay? Well, my name is Sanchez, as you have seen. Yeah, you can sit there. Okay. I sit here. Okay. And I'm in the research and development area of new digital business of BBVA. And today here we are going to introduce you a weapon to fight against exponentially hard problem. And please allow me the lack of rigor, the lack of accuracy, because when I say exponentially hard problems, quantum practitioners should hear MP hard problems. Okay. Well, let me give you an example of what an exponential problem in the financial sector could be. If we have 100 of assets, 100 of stocks, for example, then that's not a big quantity for a financial problem because, for example, the Standard & Poor's has 500, S&P 500, and you want to calculate, you want to find the combination of those assets that is the least risky, the most conservative portfolio. If you go one by one, the solution is a sequence of yes or no to one question. The question is this asset in this portfolio? There are 100 assets, there will be 100 questions. 100 questions with two possible answers, yes or no, okay? This sequence, if you multiply this 2 times 2 times 2 times 2, 100 times, give you the number 2 to 100. It's a huge number. In order for you to know what the extent of this number is, if you, in each of the steps, spend 1 nanosecond, that is 10 to minus 9, is 1 billionth of a second, the whole process will be thousands of times the age of the universe. That is all enough. It's 14 billion years, the age of the universe. But do not panic. Do not panic. We think that quantum has a word in this exponentially hard problem. Well, as I said, I'm in the research and development department of new digital business of BBVA. You know, in BBVA, our purpose is to bring the age of opportunity to everyone. In new digital business, we want to transform our bank. We want to be a global digital company, the first or the best digital bank in the 21st century. But not for whatever reason. We are also in client solutions, not for an arbitrary reasons. It's because we want to make the life of our clients better and easier. And we leverage on these technologies or whatever to achieve this target. In our department, we follow an approach that it's inspired by the deductive scientific approach or method to remain adaptable to the breakthroughs in society, in science and technology. But as I told you, always with the client in mind. Okay? This scientific method has 3 phases. In the first phase, you can state the problem, search the problem, investigate and research about the problem. Here the problem is exponentially hard problem. Okay? What's there? There is Moore's law. Okay, again, for the lack of accuracy, I know that Moore's law is not a law, but allow me the thing. Moore's law is facing right now, right these years, is facing the size of subatomic particle. It's not going to be anymore. It's facing the end. If you go tinier, you are going to face with quantum mechanics. And in quantum mechanics, things are strange and stranger. You will see. In the second phase of the scientific approach that we are inspired by this method, we form a conjecture, a law, an hypothesis. And it's our hypothesis that quantum is here to try to solve this problem, and it's going to have some advantage. I am not saying a supremacy, but I am saying advantage, and in our opinion, maybe as close as 5 years from now. allow me for the, again, for the lack of accuracy, that's an opinion, okay? And the third phase of the, once we have the problem, once we have the hypothesis for solving the problem, we have to test our hypothesis. And to test our hypothesis, my colleagues here are going to tell you, after my presentation, are going to tell you how are we going to try to do this, okay? So, as I told you, with this scientific approach, we always try to answer to three questions. The three questions is, what are we trying to do? As I told you before, we are facing tiny particles, we are facing tiny subatomic particles, and quantum has a word on this. And if quantum has a word on this, because in the things like electron crossings, physical barriers happen at these tiny sizes, okay? The second question that we have to answer is, and the answer is that how is it done today, okay? How is it done today? How do they solve this problem today? Today, engineers can handle tiny particles better than ever in history. So because of this, we are living this second quantum revolution. That's my opinion, okay? And they are going to the qubits. It's an example with a bit. It's like if you answer your question and the answer is given by a German. It's yes or no, ja or nein, 1 or 0. On the other hand, if we consider the qubit, that is the minimum information unit for quantum computing, it's like an answer of an Spanish. It's maybe 1 or 0. I will decide when you measure me, okay? That's the difference. Well, this superposition that is called, mathematically, this superposition is nothing more than a linear combination of basic states. It's a vector space, a complex vector space. And I will not go more with accuracy because it will end, who knows. This superposition combined of one qubit, combined with the entanglement of several qubits, okay? The entanglement is, in quantum mechanics, the particles behave like this way, like entanglement. And this is mathematically a tensor product of vector space. The tensor product of vector space multiplies the dimension. Because of this, we achieve the exponentiality that we need for resolve exponentially hard problems. Okay? And the third thing that we must answer in our scientific approach is, what do we propose? After all this research, after all gathering all this data, we propose to build capabilities in quantum computing. We think that the espresso train of quantum is here. Behind the hype, that I recognize there is something hype. There's some hype in this world. Behind that, there is an espresso train. There is something very, very strong there. We have been in this line of research almost 2 years. We have been searching and researching in our line business and trying to find problems, candidates for this quantum advantage. Quantum advantage is nothing more than a problem that with quantum can be solved better than with classical. Okay, this is the thing. Well, you know, all this. As I told you before, that the quantum was the nightmare of the engineers and the dream of the scientists. Theoretically, the theoretical scientists, we know that it has advantage, that it has supremacy. Theoretically, we know it. But in practice, to put all this in practice, we need a number of qubits that engineers cannot construct right now. Because of this, it's an engineer nightmare, okay? But maybe not for so long. You know, a couple of weeks ago or 3 weeks ago, a vanishing paper. What would you expect? It's a quantum paper. It must be appearing, disappearing. It appears somewhere. Financial Times took it. A paper where Google, quantum artificial intelligence department of Google, claimed that the supremacy, quantum supremacy, is here. And well, if that is true, if their numbers are true, we also have a collateral benefit on this. If that is true, we could save in energy. Remember the sustainable development goals and climate change. In terms of energy, we could save 4 years the electricity consumption of the whole country, of the whole Spain. So the chief of this department of Google, Nevin, stated a couple of months ago a law, not a law, but a law, that said that quantum computing is increasing in a doubly exponential way. Maybe we are changing from Moore's law, that is double the capacity every 2 years, to Nevin's law, that is 2 to n, doubly exponential. Okay, maybe we are there. Well, we are not sure of all this. This is our opinion, and but there are data behind all this. There are data behind all this that are going to tell us something about that. Well, Darío Gil is the head of research in a global basis of IBM. He told in a conference three months ago in CSIC that this situation of quantum reminds him of classical computing in the 50s of the last century. I'm going a little bit more with all humility, but for me, this situation is very similar to this photograph. Do you recognize people in this photograph? Yes, this is Manhattan Project. This stage of the humanity, for me, is very similar with quantum computing right now. There was a war, there was a race. There were the Allies, there were the Nazis, there were Oppenheimer, Bohr, and the former friend of Bohr, that was Heisenberg, the one who discovered the uncertainty principle, so he was a really intelligent man, in the Nazis, trying to build the A bomb, the nuclear bomb. It was a race. Well, some bad language say that Heisenberg was delaying the project for the Nazis, and I tend to think that it was the way. Well, for me, we are in a situation like this, and can you guess what this drives to the current situation? This has changed the world, and maybe this is a tipping point also in the world. And also, when you go to somewhere, to conference, in quantum, you always see the army there. Because of that, that recalls me this situation, much that other things. Well, and we are not alone in this vision. There are. Do you remember what they say about technology at the beginning of the century? They say that in the US they invent, in China they copy, and in Europe we regulate. Okay, something is changing. Something is changing. In Europe we are still regulating, but look at these figures. The Chinese public investment. Okay, the Chinese are investing 10 billion in 5 years. The European and of dollars. The European Union and the States, more or less 1 billion. Okay, the Chinese are spending 20 times the money of the other two countries, and not only private, because if we talk about the Chinese Holy Trinity, Alibaba, that is their Amazon, Tencent, that is their Facebook, or Baidu, that is their Google, are adding 35 more billion to this equation. So think about it. And in the sectors, in the public sector of the Western industry, we ourselves have signed an agreement with CSIC, Airbus, that are there in the States, have a quantum challenge. JP Morgan and Barclays are in the IBM Q network. Anderson Horowitz investing in Rigetti. Morgan Stanley creating a quantum computer. It's a lot of people thinking about this. Okay, a lot of people doing this, and so I'm going to finish. As I told you before, problem, hypothesis, testing the hypothesis. We are now here. And we are trying to test the hypothesis with these guys, with Roman and with Enrique. This time, well, excuse me, I would prefer to use the word boutique instead of tiny, because tiny startup, remember me, what Blockbuster thought about Netflix when they offered Netflix to Blockbuster. It's a child game. Look where is Blockbuster. They went bankrupt. They filed Chapter 11, and look where is Netflix. But I don't know now, but maybe with this, even with this plunge in the stock market, but maybe there are 30 billion of capitalization. So, thank you very much for stoically endure the pain of my speech. And I will be around if you have any question or whatever. With no more question, with no more things, I will give the device and the floor to my friend, Roman.
Thank you. Okay, so very briefly, thank you, Escolastico, for this very nice introduction. So very briefly about quantum computing, because I assume that most of you are not experts in quantum computing, and therefore you need to know a little bit about the idea of what the types of things that we can do here. Is not working, the micro? Yes, no? Hello? 222? Yeah? Yes? Okay. Yeah, now it's working. Okay. So what's quantum computing about? So quantum computing is about a fundamentally different way of processing information, right? So nowadays we already use devices that to process information in our in our standard computers, and we have these devices that work with materials that we understand them precisely because we understand quantum mechanics, right? So we have semiconductors, we have conductors, insulators, then we have transistors, and so on. And this is, the reason why we've been able to build our computers nowadays. But quantum computing is fundamentally different. So here the difference is that we are going to be using the laws of quantum physics to process the information. And this is something fundamentally new that no standard computing is using nowadays. Now, the point is that by using this, we have an advantage. We can do things that otherwise are impossible. Now, it's actually very interesting because with quantum computers, we can do tasks that are exponentially more difficult. I mean, things that are absolutely impossible for a standard computer. So there is no way in some of these tasks that a classical or a standard computer will ever be able to match what a quantum computer will be able to do. Now, let me give you a very standard example in the field of quantum computing, which is factorization. Now, imagine that you want to pick up a very large number and you want to find its prime factor. So for instance, 15 is equal to 5 times 3, okay? Now this is very easy if the number is small, but if the number is very large, and in particular you have something like 2,000 bits, then it turns out that the problem is very difficult. And actually this problem is the basis for a big part of our cryptography. So nowadays, our cryptography is secure, this RSA crypto system, the one that we use when we do transactions with the bank, for instance, this is secure because this problem is very difficult to solve, okay? I mean, there is no algorithm that runs efficiently to crack this problem. Now, if you do the calculation of how much time will you need to solve this problem on a standard computer, so the best algorithm that we know, it takes of the order of 10 to the 34 steps. This is a 1 with 34 zeros, all right? And if you do the numbers on a today's standard computer, like my laptop, for instance, that they run at terahertz, clock time, you just put the numbers there, and it's going to take you of the order of 317, I think, trillion years. Of course, it means that the problem is you cannot solve it in practice, right? Now, if you have a quantum computer, there is an algorithm that solves this problem efficiently. It's called the factorization quantum algorithm, and it runs in 10 to the 7 steps. Now, if you put it on a quantum processor like the ones that Google and IBM and so on are developing nowadays that run at the order of megahertz clock speed, then essentially you solve the problem in 10 seconds, right? So this is just to give you the difference, to give you the idea that this is really a change of paradigm. So we are changing the rules of the game. Things that were not solvable at all until now, once we have a quantum computer with something around 2,000 qubits, it will be possible to solve them, right? And in particular, that's going to affect essentially every field of technology that we know. I mean, it's going to affect technology, it's going to affect cryptography, security, cybersecurity, and so on and so forth. This is a very extreme example, but it's just to give you the idea. Now, what is exactly a quantum computer? So nowadays, there are several players in the game, IBM, Google, as I was mentioning, there are others. Typically, you can imagine a quantum computer like a fridge, okay? So like the fridge at home, like where you put the vegetables, and the reason for this is that the units of information for a quantum computer, they need to be cooled down to millikelvin. Actually, the fridge looks something like this. This is the one at IBM. The whole machine is actually the fridge, and the processor is just below. It's very small. It's something like this. And that's where your quantum units of information are living. Now, the whole story is just to cool down your processor to millikelvin. Now, millikelvin is 1,000 times colder than interstellar space. So this is very, very cold. It's one of the coldest places in the universe. And this is why this is a nightmare for engineers, because how the hell do you do that, no? On a place that, you know, doesn't blow up or something like that. So that's how a quantum computer look like. The technology is starting to be ready, and this is why we are getting very excited. There are different types of quantum processors. Some processors are tailored to optimization tasks. They are called quantum annealers. Some others are tailored to more universal tasks. They are called universal quantum computers. Some others use light, okay, lasers. They are photonic quantum computers, and so on. Now the point is that we are getting to the point where we start to see things moving. Google and IBM, they say they have of the order of 52, 53 qubits, which is this unit of information. With this, we can already start to prove that there is an advantage. I mean, we can do things with these processors that otherwise are just impossible. Now, the forecast is that in the next 5 to 7 years, the field is going to develop a lot, and we'll start to have processors that will be useful to do tasks in industry that will be extremely useful, all right? This is a graphic by Gardner, which I think is very representative of what is going on here. So on the horizontal scale, we have the time to market of several quantum algorithms and quantum applications. In the vertical scale, we have the impact. And you can see that some applications of very high impact, they are already very to the left, all right? So this means that in a short period of time, kind of medium term, we are going to be able to do things already with these quantum processors that are going to be useful, right, for industry. And so the next part of the talk, so it's going to be Enrique, and he will tell you especially how we are going to be using this for finance in particular.
Thank you very much, Roman. Okay, we have been talking about quantum computer and so on. Let's have a look at what we are going to do at a really big bank like BBVA. So basically, the problem with finance is, okay, you know that we have some of the brightest minds worrying about economy, finance, and so on. But the problem, as you can say, is, okay, if these people are so clever, how come that we have economic crisis and these kind of things? This is something that should be avoided. Well, the point is economy is not so simple, it's a complex game, and not only it's a complex game, but some of the tools, some of the instruments we are using are quite difficult to master. So, particularly thinking about talking about finance, the first thing is, okay, we are in some parts of the finance, specifically in investment funds. You know that most of the investment funds today, or some of the biggest, the hugest investment funds are run by machines. They are the quantum investment funds. So they are just inside a kind of arms race between them, just to try to find the best algorithms before the competitors got the idea, and so on. Okay, not only about that, also the amount of data that we are using in the investment industry is growing a lot. I mean, nowadays you may use some of what is called alternative data, which is about Twitter conversation, threads, whatever, just to have a glimpse of what is going to happen before the quotation of the companies in the stock markets change. So we have more data, we are inside an arms race, okay, and this is something that is complicated. Second, you know that in finance we are using quite complex instruments. 20 years ago, on the 74, we have the options. It was just the summon of the derivatives and the financial instruments. Nowadays, this is something completely, it's madness. I mean, we have a lot of difficult instruments to master that when they run into some kind of problems, we can go inside an economic crisis, and this is something that has happened before. And finally, the evaluation of these instruments are quite different. Okay, with these things, the problem is, okay, we cannot detect, or we cannot predict, to say something, an economic crisis, because this is something that you cannot do. This is what is called an MP problem, just to simulate the comprehensive economy or even the finance. So this is something that we can approach, but we cannot do up until now, because we didn't have the instruments to simulate that. So what we can do with a quantum computer in a real bank, in a real huge bank? First of all, what we can do is to use the quantum computers to run some optimization code. this sounds like, okay, optimization is a quite difficult game. You may use the optimization not only for the portfolio optimization or creating new portfolios, just increasing the return, reducing the risk, or whatever. You can use also the optimization for a lot of instruments. Among others, you may use optimization just to train machine learning, deep machine learning networks. We'll see more about that later. Okay, they are calling me, but I will try to accelerate. The second one is classification problems. Classification problems is quite a quite simple word. What we are talking about, this is artificial intelligence. This is, for example, fraud detection or customer behavior. So the problem is you have more and more and more data. The computer and the machine learning networks took ages to be trained, and you can use a quantum computer to do it faster and better. Pricing is the third thing. Pricing is, you may use the quantum computers just to simulate the pricing. Most of the most complex instruments, financial instruments, need some kind of Monte Carlo approximation just to compute which is the real price. Okay, this is difficult to do in the real world because Monte Carlo and the financial instruments are growing more and more and more complex, and but you can do that in a quantum computer quite easily. And finally, you may try to do that. I mean, this is about papers. This is about scientific papers we have published. How to simulate part of the economy and see what happens if you modify some of the economy rules, monetary rules, or fiscal rules. So this is something you cannot do today. Okay, in this case, the BBVA is going to use the two best approaches. One thing is just to use real quantum computers to apply to this kind of problems, and the other one is to use quantum-inspired algorithms that are coming directly from advanced physics, just to exactly to try to solve these problems today. So in this case, this is one of the most advanced approaches I have never seen in the financial industry. Okay, so finally, and thank you, because Escolastico has allowed us to just introduce 1 minute about ourselves. We are the teeny, or not so teeny startup, the boutique startup, which is Multiverse Computing. This is a paper from IBM. This is global IBM, just citing us, just the reference in quantum computing. Now, everything that you have seen there about the uses of quantum computer in finance, this is based in scientific papers that we have already published, and we are already just developing that. We have passed through some of the largest accelerators in quantum technologies in the world, which is the Creative Destruction Labs, and we are really, really, really proud to be with such a behemoth like BBVA. Thank you.